Okay, so the approach of analyzing NMRs is the first thing is you want to look at the integration. Okay, the second thing is you want to look at the location. And then the third thing is the splitting pattern, or what I call the splitification, but the splitting pattern. Okay, so remember, the integration tells you the number of hydrogens at that location, like those types of hydrogens. Are they shielded or are they de-shielded? So this is kind of where you're looking at, are they shielding or de-shielding? Shielding or de-shielding. Okay. The location tells you, it gives you an idea as possibly the types of hydrogens they are. Are they attached to something shielding? They attached to something de-shielding? There was this little slide which you might want to print out and have handy. Oh, no, actually, you don't have to worry about it. It's not going to be on the exam. But this is something that you might want to have handy when you're doing those problems, just looking at the general locations. Okay, I'll actually keep this up just so that when we're practicing these problems, we can refer to it. All right, remember here it's not posted, but these are where the aliphatic shielded hydrogens are. Then around 2 is the carbonyl hydrogens, next door to carbonyls. Then the 3 to 4 are the more electronegative. Remember, double bonds we aren't going to worry about, so nothing will have a double bond on it. Aromatics are in this region, aldehydes are here, and acids are somewhere around there. Okay? So that's kind of the location part. And then the splitting pattern. Is it a doublet? Is it a triplet? Is it a quartet? Is it a pentet, a sextet, heptet, octet, nonet? And remember, that tells you how many hydrogens are next door. This is your neighboring hydrogens. Neighboring. N-E-I-G-H-B-O-R-I-N-G. Neighboring hydrogens. Okay? So NMR pretty much gives you the skeletal structure of a molecule. Kind of shows you the backbone. Okay, so let me show you the best way to approach this. Okay? Every signal that we have, so we've got 4 signals. So that means there are 4 different types of hydrogens, or 4 different environments. You remember we talked about the environments? All right? This means there are 4 different environments. Okay? I have a formula here, C4H9Br. And remember, this is a proton NMR. Okay? So this shows me where all of the hydrogens are on the molecule. So if I have 9 hydrogens, what should the sum of all of my integration equal? It better equal that 9. Right? So there's 3, there's 6, 8, 9. So every hydrogen on this molecule is showing a signal of some sort. 3 of them obviously are equivalent and are all going at 1. Another 3 are equivalent and they are forming a doublet here at 1.7. And then there's 2 hydrogens that are equivalent. It's showing a 1, 2, 3, 4, 5, a pentet. So it's split into 5. And then here's another one that's split into 1, 2, 3, 4, 5, 6. Into a sextet. All right. Remember, if you have a little tiny peak, and if you're not sure, look on the other side. If you have the identical peak on the other side, then they are peaks. All right. Okay. So that's kind of how you know if those peaks are real. Okay. So what I do is I start at the hydrogens at the most de-shielded, because this gives me the most information. This is just basically telling me that it's aliphatic. That's all it's really telling me. But this gives me the most information, okay? So what I always do is I write a carbon with 4 groups on it. Why? Because we know this is an organic molecule. Hydrogens are on carbons, and carbons always make 4 bonds. My job is to fill in all of these spots. What are these spots? Are they hydrogens? Are they halogens? How many? Or are they carbons with a certain amount of hydrogens next door? That's what this all tells me, okay? So I first start with the integration. Integration is 1, so that means this carbon has 1 hydrogen on it. Okay? So I'm done with the integration. Next, location. This is way up at 4. So that means it's very de-shielded. So what is this carbon? What does this carbon have to be attached to? If you want to put it in the chat room. The bromine, exactly. Why is it attached to the bromine? Well, that's the only electronegative atom on my molecule. And this is way up at 4, so that means this hydrogen is feeling the effect of an electronegative atom. So bromine must be attached onto this carbon. All right, so the question is, what are the other 2 spots? Well, that's what the splitting pattern is going to tell me. It tells me about the neighboring hydrogens. Okay, I'm going to write those in red. So my splitting pattern is a 1, 2, 3, 4, 5, 6. It's a septet. So how many hydrogens are next door if I have a splitting pattern of 6? 5. Correct. Remember, it's the n plus 1 rule. This number equals n plus 1, where n is my neighboring hydrogens. All right, so remember, it's always one less. Okay, so how does this carbon how is it possible to have a carbon with 5 hydrogens next door to it? Well, I got to have 3 on one side, and I got to have 2 on the other. Does that make sense? I know this hydrogen is feeling the effect of 5 hydrogens. That's the splitting pattern, and it's basically how splitting occurs is the magnetic field of these hydrogens have an effect on the magnetic field of the neighboring hydrogens, and that's why that peak is split into other peaks. So that's what the splitting is. It's the effect of the hydrogen magnetic fields next door of the blue hydrogen. So that means this one peak gives me this amount of information. Now, as far as that CH2, I don't know what's attached to that, but that's what this information will tell me. So this one peak basically gave me the whole entire molecule, or about 80% of the molecule. Notice it gave me 3 of my 4 carbons, so I've accounted for 3 carbons. I've accounted for 3, 4, 5, 6 hydrogens and a bromine. So all that's left is 1 carbon and 3 hydrogens. What does that look like to you? All right, in this case, I don't really have to go any further. What do you think is attached onto this green part of it? What group do you think it is? All right. I'll let you guys answer. I kind of showed you the answer right here. Yeah, it's a methyl group. So that's the structure. I really don't have to go any further, but I'm going to, because not every NMR is that easy. It's not like where I get most of it and all I have to do is figure out one piece. Okay, so I'm going to erase this green part. But I just want to show you that you don't really necessarily have to analyze everything if it's pretty obvious as to what is left over. But I want to make sure everybody understands how I got this whole entire thing just from that one peak. Because, like I said, analyzing this peak, our most downfield peak, gives you most of the information of the molecule. Okay? So let me go over it again. I go over these 3 things in this order. I always draw a carbon, okay, with 4 groups around it. I first put how many hydrogens on it that is based on my integration, because that's how many hydrogens are in this location. Then I look at the location and I write any information that's given based off of that. The information here is that this hydrogen is next to something very electronegative because it's way up at 4. Well, by looking at the formula, I know it's a bromine. If I did not give you a formula, you would have no idea what that atom is. It could be a halogen, it could be an oxygen, it could be a nitrogen. You would not know. I would have to give you more information. Okay? All right? So that's how I knew that one of these other bonds has to be a bromine, because it's up at 4. The location is telling me that, and the formula tells me it's a bromine. If this was a chlorine, then obviously I would have a chlorine here. Okay? And then the splitting pattern, since it's a splitting pattern of 6, means there are 5 hydrogens next door to this carbon. So the only possible way to do that is to be 3 on one side and 2 on the other side. All right? Can you guys hold on just 1 second? Okay, so any questions on how I got this fragment? I will analyze all these just to kind of show you the process. But we pretty much have figured out the structure. But again, that doesn't always happen that way. Okay, let's go to the next one. The next one, again, carbon with 4 groups. First, I start with the integration. There's 2 hydrogens. So I'm going to draw the 2 hydrogens. You can draw them however you want, either up above each other or side to side. So if you didn't know the structure, would you just put an X? Yeah, yep, that's exactly right. You would put an X. However, you will always know the structure, because if I asked you a question saying, give me the structure of this, you would obviously have to know what X is. But if you, I don't know, have another class and they don't tell you, you would put an X, and somehow there would be more information in order to figure it out. But yep, exactly. I would just put an X there. Okay, so it's 2 hydrogens. I got the 2 hydrogens. All right. Location. Location is 1.8. So that's telling me, let's see, let's go to the 1.8. It doesn't tell me anything interesting. 1.8 is right in this location, which remember it's not written here, but in this area, this is approximately where your aliphatics show. So it's not attached to really anything. It's attached to other carbons and hydrogens. All right, well, I know it's not attached onto a halogen, so I don't really have to write anything. I then look at the splitting pattern, and I have 1, 2, 3, 4, 5. All right, I've got a pentet. I've got 5. That means there are 4 hydrogens next door to it. Remember, it's always one less. All right, 4 next to it. Now, here's where we have to think a little bit. There are 2 possibilities for that. What are the 2 possibilities of having 4? One is having a CH3 and a CH. I'll just do this. And a CH, where these, I'm putting a squiggly line, meaning I don't know what they are. That's one possibility. The other possibility are 2 CH2s. The squiggly line is attached to it. Is that correct? Am I following that? There's 4. Those are the 2 possibilities. Here, there's only one possibility, a CH3 and a CH2. I can't have a CH4 and a CH, right? That's impossible. Okay? So one of these is correct and the other one is not. So how do I know? I got to look at the other structures of the pieces I have to figure out which one it is. All right? And which one is it, guys? Is it the top one? I'll call that the A fragment, or is it the B fragment? You actually know the answer. You are actually able to figure this out based off of everything that we've done. Which one would it be, the A fragment or the B fragment? The A fragment. Right, good. Right, we know it's the A fragment because look at this molecule. What do we have here? We have a carbon with 1 hydrogen. Okay? All right, and this is implying that next door to the CH, so this CH2 fragment right here is the same as that CH2 fragment. So this signal on the NMR is for those hydrogens. This signal, remember, is for that hydrogens. So what you're doing is overlapping these fragments, trying to figure out where are these fragments on the other fragments I'm making. So that CH2 is that CH2. This CH is for that CH. And this is telling me what is next door in this green area. So this is telling me that I have a CH3. It's confirming I have a CH3 based off of that splitting pattern. Okay? So it's kind of a puzzle. This is a puzzle. What you're basically doing is analyzing each peak. Then you have to piece them all together and find out where they overlap each other. Okay? So this peak right here, analyzed for this hydrogen. This peak right here, these two, analyzed for these two. Now notice, look, I have a CH3 and a CH3. So if I look at the NMR, I should have 2 more signals, both with integrations of 3, which is exactly what I have. Okay? So notice this one, so let's analyze this. This is 3 hydrogens. How many hydrogens is next door? Now, as far as location, again, it's aliphatic. But how many hydrogens are next door of these 3 hydrogens? So I have to fill in the piece right here. 1. Exactly. I'm going to put a squiggly line here. Why is it 1? Because it's a doublet. I got a doublet. So that gives me that. So remember, it's always 1 less. And then this is a CH3 next door to what? So it's a triplet. What's it next door to? CH2. So this peak is for that hydrogen. And then this peak right here is for this hydrogen over here. Okay? this is how you should analyze these. This is a systematic way, very linear, systematic way of doing these. But you have to think about this. You have to think about where the fragments are overlapping. You know, have I seen a CH2 next to a CH? I have on this fragment. Okay? And then everything just kind of falls into place. Usually, by the time you analyze 2 of the peaks, at least the molecules I'm going to give you, you should be able to figure out most of the molecule, or pretty much figure out the molecule. Okay? We are going to do a bunch more of these in the same process, but I want to make sure everybody understands the process, because that's the starting point. If you have a starting point process, you can at least try to get it. Okay? But these are the 3 things you always have to think of. First, the integration. First, write how many hydrogens there are. Why don't we do another one? Why don't I do it with you? And then I will let you guys go. Let's do this one right here. Grab this one. I'll tell you what. Why don't you guys work on it first? All right? Work on it first. Struggle on it first. Maybe I should say it that way. It's okay to struggle. That's how we learn. You learn by making mistakes. That's why I have learned a lot in my life. Okay, so let me put number 1 here. First thing is integration. I'll put I'll put it. 2 is location. And 3 is splitting pattern. Okay, so remember, on the location, go back to this slide. Look at that. You're welcome. All right, and right here, I'll just draw it here because it's not on here. I wish they. So remember, right roughly around here are the aliphatics. Okay. Okay. So start at this peak here. Okay. Remember, draw carbon, 4 groups. Same thing here. Draw a carbon with 4 groups. Draw carbon, 4 groups. Carbon, 4 groups. Start filling in all the information on each carbon that relates to the corresponding peak. Okay, so for right now, I just want you to do that part of it. And then see if you can come up with the structure, and then we'll go over it, all right? I'm going to put it on pause. Okay, so one of the things that I like to do first, even before this, so obviously these 3 things are important. But the other thing I like to do, which I think helps out quite a bit, is to try to think about what the possible functional group of the molecule is before I even do anything. Okay, so I look at my formula: CH5, H10, and an O. So I have 1 oxygen in here. So I think to myself, what possible functional groups have 1 oxygen in it? Okay, and they are an ether, an alcohol, a ketone, or an aldehyde. So that means this molecule has to be one of these 4 structures. Okay? And what I like to do is see if I can narrow it down to maybe 2 of them, or possibly even figure out what it possibly is. Okay? So I'm going to first start with the aldehyde. I know this cannot be an aldehyde. How do I know this can't be an aldehyde? Right? This all goes to kind of looking at the location part of it first. All right. Well, aldehyde hydrogens show up between 9 and 10. All right. I don't have a peak. My highest peak is at 2.4. So I cannot have an aldehyde. There is not an aldehyde in here. Okay. What about possibly an ether? All right. So an ether would imply I have a carbon with a hydrogen next door to an oxygen. Well, that shows up between 3 and 4. Do I have a peak between 3 and 4? I do not, because 2.4 is my highest. So I do not have an ether Also, an alcohol would give me the same thing. The hydrogens attached to a hydrogen next to an alcohol would also show up between that 3 and 4. So just based off of this, I've already figured out that this molecule has to be a ketone. Now, it doesn't always work out this beautifully. Sometimes it's like two possibilities. Well, maybe it's an ether, maybe it's a ketone. In this case, there's no doubt it has to be a ketone. Otherwise, for these two, I would have peaks between the 3 and the 4 range. I don't have anything there. Okay? The aldehyde, I'd have something between 9 and 10. I don't have anything there. Okay? And then a ketone, just to kind of see where hydrogens would be next door to a ketone, all right, that is between 2 and 3, right there. And guess what? I've got peaks in that area. So sometimes that helps. Sometimes it works very nicely like this. Sometimes it's not as nice. But I would start with that first. Look at your formula. See if you can eliminate functional groups so that you have an idea as to what it possibly can be. So I already know this is going to be a ketone. All right, that makes sense? All right, can't be anything other than these 4 things. There is no other functional group that you have learned that has 1 oxygen that is other than these functional groups. I mean, I guess it could be an epoxide, but an epoxide is a type of ether. So I guess if you wanted to put epoxide, but again, I would see peaks up in the 3 and the 4 range. Okay, so if you didn't get a ketone, all right, this is something you might want to do at the very beginning. Look at your formula and see if you can maybe figure out what it possibly is. If I had 2 oxygens, then I'd be thinking maybe an ester, maybe a carboxylic acid. It could be 2 alcohols or 2 ketones or 2 ethers or a ketone and ether. It could be any of those possibilities, but if you look at the locations of things first, that might give you an idea. Once you kind of have the idea, then I would go ahead and do all of this stuff and try to figure out what the structure is. Okay. Now, if you had an IR, there are a few problems here where I do have IRs in them. You can look at the IR, and if you have a carbonyl peak, then you automatically know that you have either a ketone or aldehyde. It's not an ether or an alcohol or anything else. Okay. So I'm slowly trying to show you all the ways in order to analyze this. I mean, if I just showed you everything at once, it'd be overwhelming. It probably is already overwhelming, but while practicing these, I'm trying to give you some of the little secrets. And this just comes, again, with practice and doing this so many times. Okay, so knowing it's a ketone, let's start here. I've got a molecule that has 2 hydrogens, so I'm going to put 2 hydrogens. Okay, it's roughly at the 2.4, so that's implying that it's a hydrogen next to a carbonyl. So I probably have a carbonyl on one side, because a carbonyl does not show up on the hydrogen NMR because there is no hydrogen on this compound, on this group. So this has to be assumed. This is something you have to figure out based off of this. There is no hydrogen. There is no peak here that tells me it's a carbonyl. This implies I have a carbonyl. These peaks in the 2 range, it's implying I have a carbonyl. And then it's a doublet. So what does a doublet mean? A doublet means I have 2 hydrogens next door. Well, that means I must have a CH2 right there. Okay? Well, if you guys notice, that's pretty much most of my molecule. I can pretty much figure out what's going to happen from here. All right? Because I'm missing 2 more carbons. Well, obviously, one of the carbons has to be here and the other one has to be here. Okay? But let's just keep analyzing just to make sure that we understand. The next one, I'll do this in red. This is 3 hydrogens. So 1, 2, 3. All right, and it's next door to 0 hydrogens. Okay, so it's next door to 0 hydrogens, but it's at this 2.2 range, 2.1, which means it must be next door to the carbonyl. So that means this empty spot right here is probably the carbonyl. Not probably, it is. So that means this empty spot right here is a CH3 group. All right, so I'll start piecing it all together. So I got a CH3. Okay, and then from the blue fragment, I got this, a CH2 and a CH2. Well, if you look at the formula, all I have left is a CH3 group is left over. So I think it's pretty obvious as to what it is. But, like I said, let's just go through everything to make sure you understand how to analyze this. All right, this has 2 hydrogens, and now to the splitting. 1, 2, 3, 4, 5, 6. 6, so remember it's less 1, so 5 hydrogens. That means I have a methyl on one side and a CH2 on the other. All right, so these hydrogens here are implying these hydrogens here. So that means I have a CH3 here, because that's what this is telling me. And then, just to finish it off, I have 3 hydrogens. And since it's a triplet, right, 1, 2, 3, that means there are 2 hydrogens next door, so CH2. So our CH3, CH2, notice CH2, CH3, so this fragment overlaps with this fragment. So those are overlapping fragments. This CH2 and this CH2 are these two CH2s and CH2s. That's an overlapping fragment. And then this carbonyl and this empty spot is the overlapping fragment for this carbonyl and the CH3. Okay? So I got most people saying that they were ready. Is this what you guys got? I know one person got it. I think Anna gave me the structure. She privately gave me the structure. So thanks for doing that, for doing it privately. So, yep, I know Anna got it. Other people get it. Make sure you guys are on the right track. Or if you guys have any questions, if you guys have questions as far as this part of it that I did at the beginning, that really, really helps. If you can, by process of elimination, figure out what functional group you're even working with, then you can kind of piece it all together. If you're just like, I don't even know what functional group it is. Well, you do, based off of knowing organic chemistry. All right, so again, here's why I constantly ask you guys about functional groups, because this, I assume you already know this, that one oxygen molecule has to be one of these 4 functional groups. Okay? So anything? You guys good? If I hear nothing, I'm going to assume that's a good sign. Good. All right. Hey, Kelly said she's good, so we're good. Okay, so I really don't want to erase that. So no, let's do this thing. That'll work. Okay, let's do another one. Where was it? It's this one here. Right there. Let's get the Dandy copying tool. Copy. Copy. Okay. Go for it. And I'll let you guys work on this. Okay, so I got 2 oxygens. So I think to myself, what functional groups are there? There's esters. There's an ester. There's a carboxylic acid. Possibly 2 ketones, or 2 aldehydes, or 2 ethers, or 2 alcohols. Most of these, pretty obvious. I can ignore. So I know it's not an acid because I would have a peak at 11 to 12. I don't have that. All right. 2 aldehydes I don't have because I don't have peaks up at 9 or 10. It can't be that. Okay, if it was 2 alcohols or 2 ethers, all right, remember that would mean groups up in this 3 to 4 range. I only have 1 group in the 3 to 4 range. If I had 2 of these, I would have 2 groups in the 3 to 4 range. But I only have 1, so it can't be these. So this implies I've got 1 group where a carbon hydrogen is attached to an oxygen. And then notice I got 1 in this 2.5 range, which is carbonyl. So a hydrogen next to a carbonyl. So this tells me this molecule has 1 group that looks like this and another group that has a carbonyl on it. So that would imply to me most likely an ester, though it could be an ether and a ketone. But since I only have 4 carbons, it probably isn't both. All right, and usually based off of what we've seen in organic chemistry, ester is a common functional group. So I'm guessing this is an ester. So that's where I'm going to be thinking, but I'm not ruling out a ketone and an ether. So it could be possibly, a ketone on one side of the molecule and an ether on the other, but since I only have 4 carbons, that might be impossible to do. But I'll make sure you guys understand how I'm even coming up with that. All right, I'm looking to see what my groups are. And that helps me analyze these. All right, so let's start here. I've got something with 3 hydrogens on it. All right, and it's attached to the thing that's the most electronegative because we're way up at 3.5, so we're right around here. All right, so we're looking at a group like this, so that means the oxygen has to be attached there. So that's what that fragment tells me. This one tells me I have 2 hydrogens. All right, this is at the 2.5, so this must be next to a carbonyl. And on the other side, since it's a quartet, I have 1 less than that. I have the CH3 attached to it. All right, and that's 4 of my carbons, so I pretty much have all the fragments to it. Basically, you just attach that right there. But just to analyze this is a CH3 next door to a CH2. Because I have 3, all right, and it's a doublet, so it's 2. So my molecule is methyl propanoate. Oh, there's an oxygen right here. Remember, in naming it esters, methyl, and then 3 carbons, propanoate. That good? Everybody get that? Good. Anna says yes. Ashley, Luke, good. Jacob, good. Jade, good. Very good. Good. You guys finding this fun? Some people do. It's like a puzzle. It's like, you got information, you just got to piece it all together. I know you guys are finding it fun. And I know you're not answering that. I know you do. You just don't want to answer it. Everything is more fun when you start to understand. Yes, that's true. It is. All right, let's do this one. We're going to do this. Well, I'll give you guys a chance on this one. This is a little bit more complicated. We kind of, went from, first grade to about high school in one jump. But I think you guys can do this. Splitting might be hard to see, but try your best at it. Again, based off. Okay. I don't know what just happened over weird. Unfortunately, can't make it any bigger. So that's the biggest it can be. The formula is C11H14O2. we're distinguishing the peaks. So again, think about Pascal's triangle. So remember, if you have an even number, odd number, just look for the blips. I'll give you this hint. In this region right here, in the 7 to 8 region, don't worry about the splitting pattern. Just look at how many hydrogens total are in that group. Okay, don't worry about the splitting in this region. Just worry about the splitting at the 4, at the 1.5 and the 2 and the 1. Okay, and I can clearly see that there's one big one here, then there's 2 on each side. This one, there is 1 here, 1 here, 1 here, 1 here, and then again, if you have one on one side, you got to have pretty much an equal one on the other. So 1, 2. So this one has 6. 1, 2, 3, 4, 5. There's 5 on that one. 3 there. Don't worry about the splitting here, and that obviously is a singlet. Yeah, maybe we'll do this. Maybe we'll. I know what we'll do. How's that? I'll leave that one over. You guys should be able to see that one pretty well. Now you should see the splitting. Yeah, there we go. And this one up here is 3. That's in the, there we go. There we go. Got it all in there. Give you guys about 3 more minutes, just because time-wise, we gotta make sure we have enough time until 2 o'clock. Today, I really wanted to spend on this. However, if there's a how to make this, it might seem complicated, but when we start analyzing it, you'll see how it's pretty straightforward. Okay, so the first thing is I have 11 carbons and I've got 2 oxygens. Okay, so whenever I have a lot of carbons, I always look in this region right here first, because believe it or not, this tells me half of my molecule just like that. Okay, what peaks show up in this range? The aromatic ring. So I know these hydrogens is for an aromatic ring. So, and there are 2 hydrogens on it. Now, you don't have to worry about what the substitution is, but if you ever see, this is just more information, but you don't need to know this. If you ever see 2 of these, a doublet and a doublet, that means that my substitution on my molecule is para. Because since it's a symmetrical molecule, it shows that on the NMR. But if you put it as ortho or para or meta, it doesn't matter. As long as you knew it's a di-substituted aromatic ring. And the way we know it's di-substituted is how many hydrogens total are on a benzene. There are 6 hydrogens total. Well, if this is telling me a total integration of 4, that means 2 of the hydrogens are gone. So that means 2 of the spots on the aromatic ring have groups. Okay? So that's what that tells me. You don't have to worry about the splitting. So if you put ortho or para or meta, it doesn't. I'm not going to grade incorrectly because this is more information. There are other splitting patterns that show a difference, which we're not going to go into. But if you just group all these peaks as 1 and you have an integration of 4, so I have an integration of 4 because it's 2 plus 2, that means I just basically have an aromatic ring that's a di-substituted ring. If this was 3, if one of these is a 3 if one is a 2 and the other one is a 1, what does that imply? So a 2 and a 1 implies I have 3 hydrogens on my aromatic ring. So that means it's a tri-substituted aromatic ring. Does that make sense? So aromatics are easy. It basically tells you, so that tells me 6 of my carbons. So I don't have to worry about 5 more carbons on my molecule. Okay? Then I look at this and I have 2 oxygens. So look at this peak right here. This peak at 10 with 1 hydrogen. It's a singlet. That tells me aldehyde. Okay? So I've already kind of figured out most of this molecule just by these two peaks. All right, so the other oxygen, it's one more oxygen. It's either an alcohol or a ketone or an ether or something like that. Since I have a peak way up at 4, that's maybe implying an alcohol or maybe an ether. Okay, because our peak at 4 means I have a carbon that's actually attached onto something electronegative. Okay, but I don't have a single peak for an alcohol, so I kind of know we can't really do that. Okay, does that make sense? This half of the NMR pretty much tells me the majority of my molecule. I don't have to worry about splitting patterns or anything like that. This tells me di substituted, okay, because I have 4 hydrogens. I have a total of 4 hydrogens, all right? And then this tells me I have an aldehyde as one of the carbons. Okay, so 6 carbons have been accounted for in the aldehyde. So 6 carbons have been accounted for. 4 hydrogens here and 1 hydrogen there. 5 hydrogens have been accounted for. And an oxygen have been accounted for. So what's left over? Well, C5H9O is left over. Okay, and just to double check, 9 hydrogens. So 2 here, 2 here, 2 here is a total of 6. Plus another 3 is 9. So this is now the formula for these peaks. And now I'm going to do exactly what we learned previously by starting here, doing the integration, the location, and the splitification to kind of figure out what this fragment is going to be. And then we piece it all together. Does that make sense? So at first it might look like it's very complicated, but if you break it up in this NMR, that's kind of why I have a space here to kind of break this up, showing you that this top half, you don't really have to worry about any of the splitting or any of the other stuff. It's really just giving you a lot of information about your molecule. Aromatic aldehyde. All right. This, anything lower than about 5 is when you have to really worry about the splitting and the structure and all that other stuff. Okay. So we'll start here. Let's do this in blue so we have contrast here. So I'm going to do it up here. So the one at 4 has 2 hydrogens. All right, since it's up at 4, it's attached to an oxygen. It's directly attached to an oxygen. And since it's a triplet, it's next door to 2 hydrogens. So this fragment is for this peak right there. All right, so that's for 2 of these 5. So I have 3 carbons left to worry about. And then 5 of the hydrogens and the oxygen. Okay, now let's go here. We've got a CH2. All right, it's pretty much in the aliphatic range, so it's not attached to any oxygens or anything. However, the splitting was 1, 2, 3, 4, 5. The splitting was 5, so this is next to 4. So it's either a CH3 and a CH, right? Or it's a CH2 on one side and a CH2 on the other side. Most likely it's this one. Why is it that one? Based off of this fragment right here. CH2, CH2. So most likely I have a bunch of CH2s hooked onto each other. All right, plus if you look at this, 2, 2, 2, probably a CH2, a CH2, and a CH2. So, because this would imply I have a carbon with only 1 hydrogen on it. Well, there's nothing down here that has a hydrogen or a group that only has 1 hydrogen on it. So it's probably not that group. And then we have this one, which is a CH2 next door to a CH2 and a CH3. Because this is 1, 2, 3, 4, 5, 6. So 5 hydrogens, CH3 and CH2. And then we have our CH3 attached onto our CH2. Okay, so the molecule, I don't have any more room, but so where does the aldehyde fit in? Well, remember there are 2 groups on here. One group is probably the aldehyde, so that's probably our aldehyde right there. And then this gigantic group that has the CH3, CH2, CH2O is hanging off of our ring here. So CH2, CH2. Oh no, I'm sorry. I gotta get the oxygen in there. So oxygen, CH2, 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 CH3, 4, 10, 11. Does that make sense? Did anyone get that? I want to see if this is a little more challenging because we haven't seen anything like this. But now, hopefully, by seeing this, by seeing these things, it makes it easier if you break up NMRs in two pieces. Realize that this upper half, anything above 7, you don't really have to worry about splitting or anything. It's just basically aromatic that's di-substituted. That's what you get from here. And you have an aldehyde. Now, let's just analyze this part. So if you ever get an NMR, I would just kind of split it up, and things to the left is very easy. Aromatics, aldehydes, or carboxylic acids. That's basically the only thing that you get from that. But it's this that really starts telling you about our backbone of our carbons here. Okay, and then another way of checking this, just to double check you have the right groups, what you want to do is make sure that your groups with the number of hydrogens match your integrations. Right? So this says I have 3 hydrogens. Is there something that has 3 hydrogens on it? Yeah, I got a CH3. Then notice I got a CH2, a CH2, and a CH2. CH2, CH2, CH2. One of them is up at 4, so that means that must be attached onto the oxygen. And these two are pretty much aliphatics, or attached onto each other. And that's what I see. 2 aliphatics and then 1 that's attached onto the oxygen. So I mean now, when you look at it, it all fits together. Then I got an aromatic with 4 hydrogens. Here's my aromatic with 4 hydrogens. So the aldehyde must be all by itself, hanging out at the other spot. Okay. Now I know I didn't give you guys a lot of time, but were people kind of on this track? I want to get an idea. Mostly? Okay, good. Yeah, I'm going to give you a lot of time just because I want to make sure I go over everything. Okay, as long as you guys were kinda, need more time. Yeah, but as long as you were kind of on the track, but I kind of just wanted to show you this trick. In knowing this now, it might make these types of structures go much quicker, especially the aromatic. So when I get an NMR, so the first thing I look at is if I have aromatics or if I have an aldehyde or a carboxylic acid. That's the first thing, because I can knock out half of my molecule or most of my molecule in one shot. Then, because this I think is the more complicated, is looking at the splitting patterns, trying to figure out what things are attached to, how many are next door. This is the stuff that really you have to focus on more and pay attention. This stuff is the easy stuff. Okay? Yeah, it is a good trick to know. I mean, that's the thing. It's years of doing this. You know, you finally get all these tricks. You guys, it's the first time seeing it, so you know, it seems so obvious, but I understand it might be very overwhelming the first time that you're seeing this. A lot of information. It's kind of like, when do I use this and when do I use that? So, I know. That's why I'm giving you guys more time in order to work on it. This way, I want you to enjoy the process in a way. Okay, let's get this all out of here. All right, let's go to some more. Let me make this one. Okay, this one. This has an IR and an NMR and a formula. That should make it really easy. I think there's this one and one more after this. All right. Okay, so because I wanted to get IR practice, because we did IR practice last week, so I want to kind of get back to some IR practice. Here's the NMR down here. Hopefully you guys can see it. I'll blow it up a little bit bigger. But I wanted to keep this down here so you guys at least have this handy. Okay. This is offset. It doesn't tell me where. That's interesting. Oh yeah, it does. It's between 11 and 12. It's telling you that that's between 11 and 12. You can't see it. It's this little blob right there, but it's showing you that. Okay, so what I want you to do is analyze the IR. Write down everything you need to know, because when you got, so this is kind of what I'm going to give you as far as the exam part of it. That's due Monday. I'm going to give you an IR and an NMR. You might not get the answer, but analyze as much as you can, and I'll give you partial credit. So if you say, this peak here or whatever is an aldehyde peak, and this is aliphatic, and this is aromatic, you write down all the information, I'll give you credit for all that stuff. If you just show me a structure and it's wrong, I can't give you any credit for anything, because I don't know if you analyzed everything. So write down, all right, this peak here is telling me this. This peak here tells me that. This peak here tells me that. This peak tells me this. Here's the fragment for this. So that's kind of what you should get in the habit of doing, okay? So go ahead and analyze this. This shouldn't take long. I'm hoping it's not going to take long. So here's I'll show you the, I guess you have to see everything, but I'll just tell you. I think you see it. This is a triplet, and this is a quartet. So let's put right in a triplet, and this is a quartet. Can you even see that? Oh, is this on? Oh yeah, okay, good. This is a quartet. Just put a Q up here. Because I have one more that's more stuff to it. All right, so the first thing, gigantic blob. All right, that should immediately, as soon as you looked at this, you guys should have said, oh man, that's a carboxylic acid. Why are you wasting my time? That's a carboxylic acid. Plus, to confirm it, look at the NMR. We got a peak between 10 and 11, and that's a carboxylic acid right there. So confirm carboxylic acid. All right. Also, we have a carbonyl peak. So carbonyl peak. So this is kind of how I would want you to analyze it and put stuff like this. Either put a carbonyl or write the word carbonyl or whatever. Say carboxylic acid. That's basically all you get from the IR. So I know it's a carboxylic acid, and I got a carbonyl, obviously, because carboxylic acid is. So then I'm going to analyze this. I've got, so you put a C with 2 hydrogens on it. All right. And since it's up at the 2.5 and I know I have a carbonyl, one of these must be a carbonyl. And then it's a quartet, so that means I have 3 hydrogens next door to it. And then analyze this. This is a CH3 next door to a CH2. So there you go. That is the structure right there. Propanoic acid. Okay. Notice, I'm hoping you're realizing it. If I just gave you the IR, you'd have no idea it's propanoic acid. This could be formic acid, methanoic acid, ethanoic acid, propanoic acid, isopropanoic acid, benzoic acid. It could be any infinite carboxylic acids. You would have no idea what the structure is. The NMR now tells you which acid you have. Okay, so you see how like the combination of the two is pretty powerful. It's actually amazing that normally you can't see carboxylic acid peaks on an NMR. You see how in the actual NMR it is so flat. You can barely see it, but if you blow it up so much, you can actually see something. Okay, and remember yesterday I talked about if you have hydrogen bonding, it's hard to see. It's actually spread over a larger area. So usually you don't see a carboxylic acid peak. You have to take the IR to clearly see it's a carboxylic acid or an alcohol. Okay? So you guys got any questions on that, or is that good? Just undo this because it's overlapping my thing. There we go. Okay. All right, good. All right, I think this is the last one. Yes. Okay. I got to make it smaller. All right, that's good. See that all right? Okay, so practice. Write down everything you see. Pretend it's the like the test portion. I know it's overlapping this, but I think you guys might have this pretty much memorized at this point. And that says C4H10O. I forgot that you guys have this on a smaller window. It brings it down to a smaller window. So I just realized it's probably harder to see a lot of this stuff. Especially if you're on a a mobile device, then this is probably really impossible to see. All right, and this is going to be hard. But you see this little tiny peak right there? You guys see that little peak right there? Notice you have an exact matching one on the other side. So that is a peak. Those two are peaks. So 1, 2, 3, 4, 5, 6, 7, 8. So this is a nonette. It's called a nonette because it's 9 peaks. Okay, that's how you know if you're looking. You see, like here, you can see a little bit of a blip right there. That little blip right there. But I don't have it on the other side. So that's why it can't be a peak. That's just clearly a doublet. Oh, here's the other thing I want to mention. Well, I'll just let you do it. Otherwise, I'm going to be giving you answer to this thing. Okay, let's start going over this for time because I have one more I want to do after this. It looks like a lot of you are done. First thing, alcohol peak. Classic alcohol peak. Second thing, these are all to the right of 3000, so aliphatic. Which makes sense, I only have 4 carbons, so I can only have an aliphatic. These peaks, remember, are less than our 1700 or 1600, so I don't have to worry about any of that stuff. Okay, so I know I have an alcohol, all right? So on the NMR, I should see a singlet with integration of 1, roughly in the 4 range. That's exactly what I see. Right there is my alcohol peak. And remember I told you sometimes you see your alcohol peak, sometimes you don't. Well, in this case, you actually see it. Okay. All right. Now, the other thing I want to tell you is that alcohol peaks don't split. These hydrogens are not involved in any splitting. So even though it's next door to hydrogens, they don't split. So that's why I have a singlet there. I don't have a doublet or something like that. It can't see the magnetic fields of the neighboring hydrogens because it's so preoccupied with hydrogen bonding that it can't do it. Isn't an alcoholic 10? No, that's a carboxylic acid is between 11 and 12. Carboxylic acids are between 11 and 12, not alcohols. Okay. Yep. No problem. Okay. So then I'm going to start at this peak right here, which has 2 hydrogens. It's attached to something electronegative, so that must be my alcohol. And since it's a singlet, it's attached to 1 hydrogen. So I don't know. So if you want to put X's here or squiggly lines, you can put whatever you want. So as of right now, this is the structure I have. An H, a CH2 attached to my OH. So I got to figure out what these 2 spots are. Probably at this point, you can go to the formula and figure it out. So I've accounted for 2 of the carbons and 4 of the hydrogens and the oxygen. So that leaves C2H6 left. All right, so if I split it up in between 2 different groups, that's a CH3 and a CH3. So, you know, you can analyze this how you want. At this point, you can just, obviously, this is a CH3 and a CH3. Just based off of just taking what I already have minus my formula, and I can just kind of piece it all together. But we should go back and double check just in case. Okay, so this big peak here says I have 1 hydrogen. All right, it's down underneath 2, so it's an aliphatic. And when I say 9 peaks, that means it's 8 hydrogens. How in the world can I get 8 hydrogens? The only way is a CH3, a CH3, and a CH2. All right, so actually that 1 peak gave me 90% of my molecule. Gave me everything except for the oxygen and the hydrogen. All right, so notice that fragment matches that fragment. And this is, so how in the world can I have 6 hydrogens on a molecule? Well, remember, if we have hydrogens that are equivalent, they show up in the same range, right? So this is basically, if you see anything greater, 4 or greater, that means you should split it in half because you have two groups that are showing in the exact same area. So it means that you have two of the exact same groups in the same environment. Why 4 or greater? Because if I have a carbon with 4 hydrogens on it, then that's all I have. I can't have any substitutions on here, right? So I can't have 4 on one atom. So that means I'd have to have, if it's 4, that means I'd have a CH2 in the exact same environment as another CH2. Okay, right? Did I say methane? I don't know what I said. Did I say ethane? I don't remember. I don't know what I said. Okay, so we know we have 2 CH3s. I'm sorry. Yeah, we have 2 CH3s for those 6 carbons, and they are attached. Both are attached to a carbon that only has 1 hydrogen on it. That's why it's a doublet. Does that make sense? I'll do it here. So I have a CH3 on one side and a CH3 on the other because it's all symmetrical. They are attached to a carbon that must only have 1 hydrogen attached to it because it's a doublet. So you see this a lot, a 6H doublet. If you ever see a 6H in a doublet, that means you have a hydrogen that looks like that. Once you do these so often, you'll see these types of patterns over and over again. And as soon as you see this now I don't expect that to happen to you guys because you guys are only going to study this for another 4 days. All right? But when you've done it 20 years, like I've done it, I see this, I'm like, oh, that is an isopropyl group. That's implying an isopropyl group, right? Isopropyl, where you have a CH3 and an H. That's an isopropyl group. So that's kind of a trigger at this point. Okay? Make sense? Okay, there is another problem we don't have time to do, but it's the problem on the slides. It's the very last problem right here. Once you guys do this on your own, you can either email me the structure or I'll actually post the structure. But I want to give you guys a chance to actually work on it. But basically how this looks is, here's the formula. All right, this peak right here, here's the blow up for it. It shows you the red line. Here's the blow up, so it's showing you a doublet. And it's an integration of 2. All right. And then this singlet down here has an integration of 3. I had to put all the integrations up here. This peak right here is this gigantic thing, all right, which has an integration of 1. And then, hey, look at this, a doublet with the 6. What is that kind of implying? Plus you have a 1. Oh, sorry, I got a meeting in 15 minutes. So we just got over telling what that kind of thing is. Okay? Well, do you guys think you can do it in 5 minutes? I'll tell you what, I'll give you the 5 minutes. Work on it in 5 minutes. See if we can do it, and then I'll go over it. We'll see how good you guys are at this point. If you guys can get this in 5 minutes, you got it. All right? You got it. And if you did it in 7 minutes, well, guess you need more work. Again, first thing I always tell you guys to do is always look at the, always look at the formula, look at the structure to see if you can maybe kind of figure out what kind of functional group it is. So I think it had 2 oxygens in it. So 2 oxygens, either ester or ketones, stuff like that. I've got 1 peak in the carbonyl region. I'm sorry, in the oxygen region attached to oxygen. And it looks like I have a peak in the carbonyl region. So it looks like it's probably going to be an ester. Okay, but we don't know until we actually do it. So, CH2, first thing, because I have 2, it has to be attached to an oxygen, because my formula says I have an oxygen, and it's at 3.5. All right, and it is a doublet, so it's next door to 1 hydrogen. That's a squiggly line, that's a squiggly line. So that's a fragment I have so far. Okay, next one is a singlet. 3 hydrogens. That's next door to no hydrogens, but it's in the carbonyl range, and I pretty much have figured out I probably have the carbonyl because there's 2 oxygens on this molecule. This one is 1 hydrogen. All right, 1 hydrogen. Yep, and here's 1, 2, 3, 4, 5, 6, 7, 8, 9. So again, that's the isobutyl group, or the isopropyl group. Well, in this case, it's isobutyl, because it's 9. So 6 there, and another 2 is 9. And then my CH3 next door to 1 hydrogen. I don't really have to write that. So piecing it all together, looks like this. So this CH right here looks like overlaps with this CH. And then here's the CH2 attached to an oxygen. So this CH2 is attached to the oxygen. So this fragment overlaps with this fragment right there. And then all I have left is the carbonyl and the CH3. So that's what must be on the other part of this. So your final molecule, just right up here, CH3, CH, CH3, CH2, O, carbonyl, CH3. Okay? You guys get that? Close to it? Good. Anna, great. Awesome. Very good job. Nice job, Ashley. Good job. Garrett, no. All right. It's just practice. As long as you're laughing, Garrett. I have my O in the wrong side. Okay, so hey, Jacob, that actually happens a lot. Try to think about what would happen if you had your O here. So you had your O, you had this instead, CH2, carbonyl, O, CH3. If you had that, these two peaks would have been switched, right? The methyl group would have been at the 3.5 range because that would have been attached onto there. So that singlet would have been at this position, and this doublet, that CH2, would have been near the carbonyl. That would have been on that side. Okay, so that stuff happens a lot. So just try to go back and see that and see, okay, if I had this, this would be a singlet with integration of 3. It would be in this location right here. So this whole part of it would have been over there, and then this whole part would have been over there. Okay, good, good. I've got to watch the de-shielding. Okay. Luke, when you say the same, does that mean that you got it, or you had the oxygen in the wrong place? Same as Jacob. Okay. Hopefully that makes sense. Work on these problems. I am still here. Please don't log me out. If you go under, I think it's IR NMR practice. I think it said log me out. Oh, shoot. But if you go under IR and NMR practice, there's lots of practice problems. I think you have most or all the answers are posted somewhere. If they're not, let me know. So I just posted, let's see, I posted these, NMR Part 1, NMR Part 2, IR and NMR practice problems, more NMR problems, and then I think if you go to NMR answers, I don't remember what they're the answers for, but it's for one of them. Okay, and I think the other ones have the answers on them. Just let me know. Sorry I couldn't get to any of the questions, but if you have questions about the final, any other questions,